As part of this series of Arup talks on building engineering, I've chosen to talk about a subject very close to me: building services design and its influence on our buildings. My title, Are Building Services a Necessary Evil?, provoked different responses. Trying to get rid of them for years was the most popular response from architects and developers. But it reminded me of something an architect colleague said. He said, structural engineers always start with bad news, but it tends to get better, whereas services engineers start with good news and then it just gets worse. It made me think that building services engineers need to say more about building services and not less, so others understand their challenges, but also the potential value of good design and installation. I initially rejected the title, a suggestion from my structural engineer boss, but on reflection, it was a very insightful view, because it has an underlying theme around all of design. So although I focus on building services today, we can also ask, is design a necessary evil? The last 10 years have been very successful in driving out inefficiencies in construction, and the industry in the UK has been transformed. But has this approach squeezed design down in order to get a fixed price? And have designers responded well to this? Are we now homogenizing design in a rush to get things built and reduce risk? The relevance for building services is to question whether we are building for ease of construction or for better performance. So my talk starts with my studies. I studied building services engineering at Reading University. It was a new course that was set up to acknowledge the coming of age of this discipline of building design, and it was ambitious in what it wanted. As you would expect, we studied mechanical and electrical engineering, the design of systems to provide heating, power, cooling, lighting, and water in buildings. But we also studied architecture, and in particular the history of architecture, how buildings have historically dealt with providing light and comfort, and how this was always an integral part of building. We took courses in weather patterns and climate, so not only understanding internal environments, but the climate around buildings and cities. We also studied the design of simple agricultural buildings. These buildings are driven by necessity and minimal cost to build and operate. They are naturally lit and ventilated to meet a very precise function. Lastly, we studied psychology, the way people behave and interact with their environment, and how design can influence our behaviour. What makes us happy or otherwise with our buildings, down to the colours we see and how we respond to controls or a lack of controls. The Reading University course recognised that building services was more than just the systems inside buildings. It was about integrating architecture, building physics and the science of buildings, the mechanical and electrical engineering in buildings, and the people. So I will start with architecture. Building services originated from machine engineering, but the business of incorporating services in buildings was always with architects. You can see this in windows and overhangs and chimneys, service stairs around buildings. These were always inherent in the architecture. But when it comes to modern building services, very little has been written, and yet it's so fundamental to architecture. Unless there is some very obvious visible feature, it is not usually discussed in this context. The exception to this is architectural historian Rainer Banham's book, The Architecture of the Well-Tempered Environment, which is really the only architectural academic text dedicated to modern building services in architecture. He said, in a world more humanely arranged, this book need never have been written, because those services in buildings that provide the comfort and well-being of humans would always have been part of the history of architecture. The birth of modern building services starts with air conditioning and a block of ice. To keep auditoria comfortable in the late 19th century, a block of ice was melted next to a fan. 1 ton of ice gave enough cooling to last the one performance. This is still the common metric of cooling capacity in the US. This started the development of air conditioning and the idea that cooling could be transferred mechanically around a building. But these services were still in the early years seen as a supplement to the fundamental control of climate otherwise provided by the mass of the building and by regulating the opening sizes. This is the Milam building, completed in 1929 in Euston. It's considered the first air-conditioned building by Willis Carrier. But even with air conditioning, there is still full access to light and opening windows. These buildings grew in scale and number, and with technology and familiarity, they allowed the freedom for design to focus on maximising the floor area and minimising construction cost, and later allowed more transparency very much advocated by modernist architecture. Advances in structure weren't the only reason for taller buildings. In fact, tall structures already existed. It was the services technology, the lifts, the artificial lighting, and the air conditioning that made building tall, habitable spaces possible. As the facade became less of an environmental regulator, buildings became wholly reliant on building services to even be occupied. Today, building services make up around 30% of the construction costs and 10% of the floor area. However, this area and cost was always previously built in as part of the architecture and not singled out. It's been taken to its ultimate in terms of expressing architecture. This is Lloyd's of London, completed in the 1980s. These buildings are highly reliant on complex control systems, but can be separated from the surroundings that they're in and the occupiers they serve. And we as building services engineers are highly skilled in delivering these sorts of buildings. This is inside Lloyd's of London. This building had one of the first fluid dynamic models built, which demonstrated that for smoke and normal ventilation, there was no need for additional fans or separation of space. You can also note from this image the level of detail in the integration between engineers and architects. This model for architecture has become normal, and it is now embedded in our training, education, as well as the standards that go with modern buildings. Any shortfalls in buildings as climate regulators are then corrected by the building services. This building in the city has a very large atrium and lift shaft on the entrance which faces southwest. We demonstrated through very detailed analysis that this would be much better as a naturally ventilated space. It has a 50-metre tall chimney above the entrance, so no cooling equipment was required and it would have been cheaper to run. However, in the negotiations with the tenant's engineer, we ended up having to air condition it. The default standards for officers left us no room for sensible discussions. I'm not discounting the glass box. It keeps improving and has evolved. At the Siemens Crystal building, the facades are sleek elevations but are a combination of solid and glazed curtain walling panels which are angled to reflect the sun and tuned to orientation. The building has low-energy air conditioning systems as a result and can also be naturally ventilated. This is very much the designers working with tried and tested products and materials, but in a different way. So to close this section on architecture, a summary of where we are. High-tech buildings evolving over time and adapting their facades and M&E systems for greater efficiency. The Gherkin has an inner facade layer and buffer atria spaces. The Crystal has a very simple facade, which is tuned to its orientation, and the latest one, the Shard, has a fully glazed double facade with automated shading. But how far does this way of building take us? To answer this, I go to my next topic, that of building science, the physics and behaviour of the building envelope, the structure, the form and heights of spaces, and the materials that make up buildings. Our basic modern assumption is that services are separate to the other building components. If there is enough space, it is the most simple solution to completely separate out layers. To make more efficient use of space, services and structure can start to be physically integrated. The Lloyd's images earlier illustrated this. However, the question of building science is how can structure, architecture, and services share function to save material and improve performance. This goes back to earlier examples where buildings provided environmental control. One thing it does, which is almost the opposite of how modern construction works, is to blur the edges between disciplines and force much closer working and less packaging, which is another challenge for designers and builders when it is easier to deal with minimised and simple interfaces. Examples of buildings that rely on science or building physics tend to be smaller bespoke buildings. In this example, the necessity for using local materials and achieving natural ventilation and light as the only form of temperature control meant using the height and orientation of the building and its form to create the right environment. The entire facade opens up and is entirely shaded to make this classroom work. And of course there are plenty of other small-scale examples of building physics at work. On a much larger scale, and particularly in our cities, there are only a few examples. Portcullis House is one, which although considered bespoke and one-off, it is an exemplar of integration of building physics and building services systems with architecture. Designed in 1994, you can read the systems and the structure in the facade, which allowed clear, open space inside and takes the services directly to the spaces they serve. The facade is tuned to the system, with clear story glazing to get light deep into rooms, but a shaded triple glazed unit which is also the return air path to keep the windows cool. The chimneys and the air handling units are the roof. Using the roof form, they catch wind at lower level and then expel it through wind-driven chimneys above. A second, more recent example shows that similar levels of integrated thinking can be achieved for more speculative offices. The concrete structure is exposed for thermal mass and works with an underfloor air system. Conditioned air is circulated through central structural columns, again for the most efficient way of distributing air to the floors. This is a project that I worked on, and I learnt that a test of whether a design team has worked closely enough together is when everybody thinks it is their design, and this is what integration looks like. It is also about building services working with architectural form. At the London Aquatic Centre, the building services work with the physics of the space. Air conditioning is only where there are people at low level, so the rest of the space isn't conditioned. The facades allow the whole space to be naturally lit and give passive solar gains to reduce energy consumption. The level of integrating performance of a system is at its best even though actual services cannot be read. Other buildings on the Olympic 2012 park have similar levels of performance integration. This is something that isn't so common outside of the UK, and it shows the UK leading in holistic design thinking. With the lure of BIM homogenising design for construction again, we need to hold on to this level of design thinking and integration of architecture and engineering. The third of my 4 topics is mechanical and electrical engineering. I'm going to talk about it in the context of building performance and the systems that use energy. Firstly, why do buildings consistently underperform on their prediction? At the design stage, there is always a detailed estimate of energy consumption for a typical year of a building's operation. And then, almost without exception, when actual metered data is taken, it can be double that original prediction. Some of this is down to assumptions about operating hours and different functions, but it is also about design and systems. Arup have a team that works on building performance, helping facilities managers understand the designs they have been handed. This team will carry out checks of systems in operation against the design. Their findings show the fundamental problem with our way of commissioning and handing over buildings, where typically systems are set up too quickly and squeezed into the end of a construction programme, but that never really get tested and adjusted before being occupied. In one example, the team saved £120,000 a year for a client by reviewing and adjusting the building management system's set points and finding issues that could only be found once the building had been allowed to operate for a while. In carbon terms, this is the equivalent to 1,300 flights to New York, but also a step closer to the original energy prediction. Most importantly, this approach puts the facilities team in a stronger position to make changes and fine-tune the building because of their improved understanding. So let's assume the building is now performing and the systems are working. Where is the energy used? It varies from building to building, but this is a typical split for an office. A third of the energy demand is for artificial lighting. Around 10% is for cooling and refrigeration. Almost 30% is on electricity to drive fans and pumps, which are part of the air conditioning. Another 10% is on heating energy, which is usually supplied by gas in the UK. And then, although this number does vary greatly, there is a base load of 10% for computer equipment. As I have already mentioned, the performance of the facade is the first step to getting it right. The facade design determines the system choice and the installed capacity, and vice versa. The more climatic control achieved by the facade, the simpler and lower the energy used. This is the Macmillan Centre for UCLH, completed last year. The facade uses a standard system which is triple glazed with integral shading blinds, with a very low air tightness. The air conditioning system's choice is then focused on clinical needs and not trying to deal with large load variations from the facade. Related to facade is lighting energy, which has the most significant impact on the energy consumption of all the elements. The biggest influence on this number, after the depth of the floor, is lighting control. By using controls for daylight, occupancy, or even introducing task lights, lighting energy can be reduced by half. The other part of the energy demand pie chart is fan and pump energy. The location of ventilation plant in relation to space it serves is very important. But equally, the ability to switch off fans when they are not needed can make a significant impact. Providing windows that open can mean being able to shut down ventilation fans for as much as 50% of the year. Finally, there is the computer equipment in buildings that generates heat. Buildings are still designed for everyone to have a desktop computer with large processing power, when in reality there is a whole mix of lower energy devices, with more people using mobile devices and moving processing power to central locations. So a design could allow for a base load and then extra capacity for localized areas for larger processors or multiple screens, but only when needed. Finally, unlike a window which can be seen and controlled directly, modern building services are partly considered a necessary evil because they are hidden and bear no direct relevance to the users. Exposing services does have its downsides, but if services are visible, both the people who maintain them and the users can see and understand their function. In this refurbishment in Tokyo, the old ceilings and equipment came out and were replaced by a simple air conditioning system. Pipes can easily be traced to their source, and new cables can be installed without having to carry out major works. Systems do not have to get more complicated to meet increasing demands on energy and comfort. Thinking about simple measures in the context of building users will have the biggest impact. It brings me to my last theme of building services. I've talked about architecture, building science, and building systems. This last theme is people. How we interact with buildings where we spend most of our time. Of course, many things affect us and our productivity, how we might feel on any particular morning, to the spaces themselves, our access to light, and the building location. But comfort stands out as one of the main issues in most occupancy satisfaction surveys. So I'm going to focus on comfort and control. If building services as a whole doesn't get enough airtime on projects, then the controls of services get almost nothing. And yet it is the controls where the building meets the user. The freedom that building services allows architecture, of which I've spoken about already, means that these systems aren't only fine-tuning, but also doing the bulk of environmental control, so have become completely critical to having a usable, occupiable building. And this has very much led to centralising control systems. With some aspects like fire alarms and security, the benefits of central control are obvious. But I would question whether temperature and ventilation should be so remotely and automatically controlled. From returning to buildings and obtaining feedback from occupants over the last 20 years, there are 3 things that people repeatedly want more of from their buildings. We want direct control of our environment, we want a quick response, and we want to understand how the building works. We are more likely to accept variations in temperature if we understand why and what we might be able to do about it. So rather than this model of control, where an operator has to be a single point of contact for, say, 1,000 users, which usually means days before receiving a response to a simple complaint, is there a more intelligent way to use our controls knowledge and the technology to go back to a more direct control for both occupants and building managers? So imagine if you could see immediately all the relevant data personalised to you, your energy use, the temperature in your space, for example. Clearly we don't need or want occupants to control everything, but coming back to the 3 feedback points of more control, quicker response, and better understanding, there is a benefit to all of us to devolve control and provide more information to occupants. Of course, the technology already exists in most smartphones, and this idea also recognises that most of the devices we install have intelligence and an easy means of extracting data. Even at a domestic level, equipment now has intelligence in the form of a processor. There are temperature sensors that collect data and will download the latest weather to know what to do the following day. So like a series of web pages, it is a series of physical devices. It is the Internet of Things concept applied to buildings. So rather than individual system interfaces for, say, lighting, heating, meeting rooms, access, all of these can communicate through one device. It's not about adding complexity, but about making information more available. For example, an office worker may want to know the best time to open the window, to save energy or just be more comfortable. And they can see this for themselves on their own device. This also helps operators. Again, not with more complexity, but by making the interfaces with controls much easier to use. We are trialling in our own office a system that takes building managers out onto the floors so they can interrogate problems directly and speak to users directly. This all contributes to a sense of control for both parties, quicker responses, and more understanding as a result of thinking differently about building services. I've tried to demonstrate that there are a number of different aspects to services, and not only the mechanical and electrical engineering ones. And all these aspects need to be engaged by engineers and their project teams to get a better quality solution. So knowing the technical part of mechanical and electrical engineering alone is not going to achieve this. There needs to be integration of architecture, structure, and services, using building science, using the knowledge from existing buildings and their performance, and understanding people. As for my original question, is building services design a necessary evil? That is for you to decide. For now, I'll leave you with a project which I'm working on at the moment. It is called the White Collar Factory. This is a photograph of the working prototype for it. It's an office building, which is a result of looking at the future of offices and posing some fundamental questions about how we design them. It touches on all the aspects I've spoken about. The working solution is a simple cooling system as part of the structure, a facade that is tailored to this to provide daylight but minimise solar gains. There are no ceilings, giving the volume back to the space with simple exposed surfaces. But more importantly than this solution, the team are thinking together, learning from this mock-up and measuring its performance, testing the space so that we can feed this back into the main project. It is my particular example of applying integrated thinking, and it has shown me that there is room for innovation on all projects and for a more holistic approach to engineering and architectural design. Thank you.
Well, first of all, I thought it was a really, really interesting talk by Mike. It's really good to understand where Mike's coming from and his background thinking. And secondly, I suppose it's good for us to see the broader thinking involved, and in terms of the White Collar Factory, which we're passionate about and we have been working on for years and years in terms of the thinking, the model, and now at last we're actually putting that into reality. It's for us it's good to see that actually all that thinking does make perfect sense, really, and we've always thought that, and we believe actually that most enlightened, intelligent providers of buildings and space should also come round to that way of thinking, because I think especially in today's day and age, in terms of looking at the triple bottom line, where it's not just about pounds and pennies. If you're investing in something that is there for the longer term, you have to look at obsolescence and longevity, and actually this thinking for this new type of office building is the way forward, because it is about simplifying. It's about being more intelligent with less, using our materials to their full extent, and focusing more on people rather than construction. It's actually the people and the end user and the occupier actually changing or giving them the tools to change their behaviour, and then actually everything then sort of flywheels from there. As long as you've got a building that is actually set up to provide all those efficiencies, actually it starts to work, because you're bringing people's behaviour, what people want to do. You're bringing that together with what the building can do, and you have a much better product, and in it a much more sustainable future that actually costs less money, burns less carbon, hopefully zero carbon. So it's inspiring to see it obviously set out in very kind of simple ways in the slides, and actually we hope that the industry moves that way.